In this video, we will talk about gamma distribution and show how to calculate gamma distribution in Poisson. The gamma distribution is the probability distribution of the time between events in a Poisson event process. The Poisson event process is a process in which events occur continuously and independently at a constant average rate. So we have learned Poisson distribution at a constant average rate called lambda. And the gamma distribution is used to model the time until alpha times occurrence of such Poisson events. So this alpha, maybe 1, maybe 2, maybe 3, is any number. So the gamma distribution density function is based on gamma function. And gamma function is also used in other statistical distribution, such as chi-square, beta. So gamma distribution is a general case of many other distributions, like gamma, beta, and exponential. Exponential distribution is also a particular case of the gamma distribution. So when we want to model the random time until next occurrence of a Poisson event. So if you want to know the random time until next one-time occurrence, so this random variable has exponential distribution. But generally, we can model the random time until next several times occurrence. So this is gamma distribution, right? And in this figure, we show several curves of density functions for gamma distribution. So this one, alpha equals 1, beta equals 1. So gamma distribution has two parameters called alpha and beta. And alpha is a shape parameter, beta called scale parameter. So for alpha equals 1, it is an exponential distribution. So this is the gamma function. So the gamma function is an integration from 0 to the positive infinite value in the real number, and inside this integration's part is x alpha minus 1 power times e minus x power. So if alpha is larger than 0, so the gamma function has some characteristic. For example, gamma n equals n minus 1 times n minus 2 until 1 times gamma 1. So gamma 1 equals 1. Here the equal gamma 1 equals 1. So that which means gamma n equals n minus 1 factorial. And gamma 0.5 equals square root of pi. So from gamma function, we can get the gamma density function, gamma distribution density function. So its formula is 1 divided by beta alpha power times gamma function of alpha, then times x alpha minus 1 power times e minus x divided by beta power. So x larger than 0. So gamma random variable is positive number because we model the time until next alpha times occurrence of Poisson events. So this time have to be positive number. And both alpha and beta are positive numbers also. The mean and the variance of the gamma distribution, alpha beta for the mean and alpha beta square for the variance. So in Python, we can use scipy.stats module and import its submodule called gamma. So next for function called gamma.pdf, cdf, ppf, rvs can be used to calculate the gamma density function, pdf for the probability density, cdf represents cumulative probabilities, and PPF means quantile, and RVS means random variance generation. So here, parameter A means alpha for the shape parameter, and a scale means beta in the formula for the scale parameter, and its default value is 1. So next we will show several simple examples in Poisson. So first we have to import modules for gamma from scipy.stats and numpy module and matplotlib.pyplot. We create an array called quantile between 0 to 0, 0, 1 to 10 represents the gamma random variable. So with the gap of 0.5. So because gamma random variable have to be positive number, so we set an array between 0 to 10. So we just set A for the shape and scale both equal to 1. Actually A equals 1, which means the exponential distribution. So we create function called gamma.pdf can calculate the density of these random variables with the parameter A equals A, scale equals B. So we can plot the relationship between random variables and associated density. So this is gamma density function with alpha, beta both equal to 1. Actually, this is an exponential distribution also, because alpha equals 1. So model the density, model the random variable x until next occurrence. So it's a random variable x from 0 to 10, and its density decrease from 1 to almost 0. And the area under this curve close to 1. So next function called gamma.cdf is used to calculate the cumulative probability for random variable. So we also set A and B both equal to 1. Then use gamma.cdf with the input this quantile, which represents the random variables. Then A equals A, shape parameter, scale equals B. Then we also plot the relationship between random variables and the cumulative probability. You can see the cumulative probability is non-decreasing function of the random variable. The probability from 0 to 1. So the third function is called PPF, which is used to calculate the quantiles, calculate the random variables from given cumulative probabilities. So this function actually is the inverse operation of the CDF, the last one. So we create a probability array called probs with the value between 0.01 to 1 with the gap of 0.1. Because probabilities cannot be larger than 1, so we set the value between 0, 0, 1 to 1. So next we can use the function gamma.ppf to calculate the random value x, also called quantiles, from the given probabilities. So we can show the relationship in the curve with the probabilities in x-axis and calculate random variables on the y-axis. So these random variables also increase with the probabilities. So for example, for the 0.6 probability, the random value almost equals 1, which means for this gamma distribution, almost 60% of values are less than 1, right? Because here is the probability. And about 80% of values are less than 1.6. And the last function called gamma.rvs is used to generate random variables. So we create n equals 32, a equals 3, b equals 2 here. So we can generate gamma random variables from this gamma distribution with shape equals a, scale equals b, and we want to generate 32, for example, 32 such random number from gamma distribution. We show these numbers. You can see the numbers almost around 5 or 6, because the mean of the gamma distribution equals alpha beta. So mean equals these numbers, two numbers multiplication. So mean equals 6. So you can see the number almost between 1 and 12, right? It's quite understandable because the mean is 6 in this gamma distribution. Thanks for watching.